We spend decades trying to write smarter code, assuming the P versus NP problem is a barrier we can eventually outthink with the right algorithm. But framing this as a software puzzle misdirects the investigation. A computation is rarely a straight line. While a standard Turing machine uses a flat paper tape, the execution space of a complex problem folds and twists into a dense geometric knot. By formalizing the space in the Lean-4 theorem prover, we find that P not equal to NP is an irreducible geometric invariant. It relies on a metric called Ropelength. We model a computation space as a topological landscape that must be traversed. Moving through an NP problem space is equivalent to pulling a single string through an exponentially expanding three-dimensional maze. Eventually, that string forms a knot, and like any knot, it has a physical minimum tightness. You cannot pull it tighter than its own rope length allows. This derivation in Lean-4 requires no outside axioms or sorry placeholders. It models computation purely as geometric architecture. Computational complexity becomes a problem of geometry, a measurement of a fixed structural boundary. To measure these computation spaces, we use the Betti signature. The Betti signature acts as a topological fingerprint. It counts independent geometric features, known as K-cycles, within the computation. Beta 0 represents the connected components, beginning as a single path. Beta 1 counts independent one-cycles, mapping the branching factor of solution paths. The model populates with thousands of these closed loops. The computation's total rope length is the sum of this Betti signature. The formalization applies a Clinamen cost. Every computational step taken across the structure adds exactly 1 unit of topological charge. An algorithm's time complexity is the physical length of the topological rope required to span all of its Betti cycles. This metric allows us to define strict complexity boundaries. The P-stratum, where polynomial time algorithms exist, operates with a topological budget bounded by n to the power of k. A P-computation is a smooth unknot, growing at a bounded rate. But an NP solution space creates a different structure, generating 2 to the power of n independent one-cycles. Tying this knot requires a rope length of 1 plus 2 to the power of n. This creates a geometric conflict. You have a physical boundary defined by a polynomial, but an object that expands exponentially. The NP space possesses an exponential topological mass. No algorithmic trick can compress that mass into a polynomial volume. The Lean code formalizes this conflict in the Betti lattice separation theorem. To prove that the NP rope length escapes the P-stratum, the code uses explicit witnesses. It calculates exact values where the exponential knot physically breaches the polynomial boundary. For a polynomial degree of 3 and input size of 10, the maximum P-stratum budget is 1000, but the NP rope length is 1 plus 2 to the 10th power, 1025. This contradiction proves the tightest NP knot exceeds the polynomial space. Because this gap exists, no polynomial of any degree can bound the NP rope length for all values of n. P and NP exist in separate topological strata. The knot is in its tightest form and cannot be simplified into a polynomial space. These findings suggest that P not equal to NP is one manifestation of a broader topological principle, the irreducibility of Betti charge. In mathematics, operations like computational compression or verification act as folding. You are attempting to fold a structure to decrease its Betti charge. Certain structures contain an irreducible charge that no amount of folding can eliminate. This principle unifies 3 of the most significant results in logic. The first is Gödel's incompleteness theorem. Gödel's work describes a Betti lattice of formal systems with no maximum level. Because every theory can be lifted to a higher sentence, the rope length of mathematical incompleteness is infinite. The second is Alan Turing's halting problem. The halting problem uses diagonalization to create a space where topological weight is undefined. Without a finite Betti value, the rope length of the halting question is non-computable. Then there is the P versus NP problem. The NP knot represents the exponential level of this same topological separation. Whether facing the self-reference of Gödel, the diagonalization of Turing, or the exponential branching of NP, the result is the same. Ultimately, the universe contains knots of information with irreducible Betti charge